Welcome back to this sixth lecture in the programming language series. We'll be looking today at fixed points. Last week we had an introduction to the lambda calculus and we saw how we could model several basic concepts of programming languages directly in the lambda calculus. However, this is not powerful enough to model particularly recursive functions, which we need in order to do any kind of interesting programming. As we'll see, the calculus is actually powerful enough to do this, but we'll have to investigate a little bit further to see exactly what kinds of constructs we need to model these features. The outline for today: first of all, we'll look at the problem of how to represent numbers in the lambda calculus. We'll be looking at the standard representation of numbers in the lambda calculus, and we'll see that in order to do this, we'll need to model recursion, and in particular, we need a so-called fixed point combinator. We'll dive fairly deep into that and see exactly how the fixed point combinator works and gives us this power of modeling recursion. Then we'll take a diversion. Up to now, the lambda calculus has been treated more or less as a dynamically typed or untyped language. As we'll see, if we try and add type annotations to the lambda calculus, we can certainly do this. However, this severely restricts the language we get. Furthermore, we can approach the kind of language we have with Haskell and model even a polymorphic lambda calculus. Unfortunately, as it turns out, our wonderful fixed point combinator cannot be given a reasonable type in such a typed language. So now, in order to model recursion, we actually have to add that as a primitive feature to our language. At the end, we'll have a very quick look at a couple of other calculi which are relevant to the whole story of programming languages. As usual, please refer to this excellent article by Paul Hudak on the conception, evolution, and application of functional programming languages, which you can access from the course website. So, let's have a look now at how numbers can be represented using the lambda calculus. Remember, last week we had a quick look at the following encodings. We can model Boolean values, true and false. Each of those are simply taking two arguments and returning either the first or the second of those. We could model tuples, or pairs of entities, as functions that encapsulate these values and pass them to any function that wants them. And we could model, consequently, functions that extract from this simple data structure either the first or the second element. We'll be using these as though they were extensions to the lambda calculus, though of course they can be represented directly in the lambda calculus itself. So this way we'll try and bootstrap a slightly more powerful language. There's a standard encoding of natural numbers into the lambda calculus. I say standard encoding because in fact there are many different ways of representing numbers in the lambda calculus. This is one of the simplest, however. That means that everything that we're going to model will be represented as a lambda expression. Expressions will look a little bit weird, but we'll see that they behave exactly the way we expect. So in order to model numbers, we need the number 0, and we need a way of creating a successor of a number. So we'll represent 0 as the identity function, lambda x.x, and the successor function as the function that takes a number n and returns the pair consisting of the value false followed by the number n. So the idea is that the successor keeps building up these tuples that are have more and more structure, each encoding and encapsulating the previous value of that number. They also have the additional value false, and this value false is going to represent the fact that this number is not equal to 0. So 1 is the successor of 0. Notice we're giving new syntax. So we're introducing the numbers as though they were primitives in the lambda calculus, but each of them is in fact a lambda expression, built up from more primitive lambda expressions. So 1 is the successor of 0, in other words, the tuple consisting of false and 0. 2 is the tuple consisting of false and 1, and so on and so on. Okay, so far so good. Let's see if they behave, or we can make them behave the way we expect numbers to behave. Well, we should be able to ask a number if it's 0, and we should be able to ask a number for its predecessor. Once we can do that, we can start thinking about doing arithmetic. So we'll simply encode the function is0 as a function we already have, which is first, which extracts the first element of a pair. Now it should be very clear that all of the numbers which are not 0 will return their first element, which is equal to false, as we saw on the previous slide. So every number that is not 0 will answer, if we pass it to is0, will answer the value false. So that's good. Now how does it behave with 0? Is0 will take the function first. Remember, the function first is lambda p.p true and apply it to the identity function. So we pass in the identity function, and the identity function gets applied to the value true and returns true. So 0 is 0, and everything else is not 0. Looks good. Now, how about predecessors? Predecessor of 1. Well, predecessor is defined as second. Predecessor of 1 simply extracts the second element of the pair, which is 0. But remember, our successor function always encapsulated the successor of a number as the value false, as the first element of the tuple, and the second element of the tuple was the number we started with, in other words, the predecessor. So it's clear that second will act as a perfectly good predecessor function and will give us the predecessor of any number which is not 0. Well, the question comes, of course, what happens if we do apply predecessor to 0? Let's save this for the Q&A Zoom session. Now, let's have a look at why we need this fixed point combinator. So far, we're able to compute successors and predecessors, so we can add one to a number and subtract one from another. That suggests that addition shouldn't be too hard to compute. Think of the way you would define a plus function. In Haskell, we could program it as follows. Plus of n and m. If n is equal to 0, it just returns m. And if n is not 0, or rather if n is greater than 0, but let's pretend we only have non-negative numbers for the moment, will be plus applied to n minus 1 and to m plus 1. n minus 1 is simply predecessor, we have that already, and m plus 1 is successor, we also have that already. And the plus function is the one we're trying to define, so we apply it recursively. Since n is not 0, we assume it's a positive number. Finding the predecessor of a finite number recursively will eventually hit the base case, so this looks like it's well defined. Pretty good. So let's see if we can translate it to the lambda calculus. So we can define plus, notice the 3-barred equal sign, that's a definition, so we're defining a macro as it were. Plus should be lambda n m, and in order to make the decision we'll apply is0 to n. If n is 0, then we return m, else we return plus applied to predecessor of n and successor of m. Looks beautiful, right? Well, don't forget this is a macro expansion. When you're defining a macro in any programming language, the macro can only be defined in terms of things you already have. Otherwise, you can't macro expand. This macro that we're trying to define here, plus, is using plus itself on the right-hand side. Unfortunately, that's a no-go for macros. You cannot define something in terms of itself. So we're missing a mechanism to define something that's recursive. Well, let's see how we can get out of this. The problem with that expression is that it uses plus, which is the thing that we want to define. Well, in other words, plus is a free name. So that whole expression is built out of things which are combinators that are closed expressions, but the thing that we're trying to define is a free variable. How do you get rid of a free variable in the lambda calculus? You bind it with a lambda. So let's define r plus that abstracts over this whole big expression and abstracts plus out. That is, we bind it. So now r plus is going to be a combinator. It's a closed expression. It's going to be lambda plus of n and m, so those are the things that we're defining, is 0, it's a combinator, applied to n and m and this expression, plus predecessor of n and successor of m. Predecessor and successor, they're combinators, they're closed expressions, and plus is bound by the lambda. That looks really good now. So now we have r plus, which is this great big expression. So it takes as its argument the function that we want to define. Well, r plus is not what we want. We want to pass into r plus the function that we want to define. So we're in a little bit of a bind here. But suppose we had that function. We don't know what it is. Let's call it f plus. If we took f plus, the function that we would like, our addition function, and we pass it into r plus, then it'll give us back, as the definition, the function that we want. In other words, r plus applied to f plus will give us f plus, if we had it. In other words, what we're looking for is a so-called fixed point. Look carefully at that equation. So r plus applied to f plus is the same as f plus. It's convertible. The arrows go both ways. Well, what exactly is a fixed point? A fixed point is nothing else than a value which, if you give it to that function, gives us that value back again. So we apply a function to a bunch of values, and all of these values get moved around, except some that are fixed point. We apply the function, and we get back to where we were before. So factorial of 1 is 1. Factorial of 2 is 2, so a function can have more than one fixed point. The 0th Fibonacci number is 0, the first Fibonacci number is 1. So factorial 3 is 6, that's not a fixed point. So functions may have one or more arguments that are fixed points, and values which are fixed points, and lots of others which may not be. And functions may not always be well behaved concerning fixed points. Suppose we have a successor function which will compute for any n plus 1. What would be a fixed point of the successor function? Let's save that for the Q&A session too. As it turns out, the lambda calculus has a remarkable property that every lambda expression has a fixed point. So that if you have an expression E, there's always a fixed point P, such that if E is applied to P, the result is convertible to P using reductions and conversions. We'll see that this is actually trivial to prove by construction. And it's a remarkable result because it relies on the magical Y combinator. Here's Y. It's this very obscure expression, lambda f, and the body of this lambda is two lambda expressions, one applied to the other, two identical expressions, the first applied to the other. And that's lambda x, whose body is f applied to x applied to itself. And then that thing is applied to itself. If that's not magical, I don't know what is. But let's see how it works. Suppose we define P, fixed point that we're looking for, to be this magical Y applied to E. In other words, we're binding F to E. So now we get the body lambda x E applied to xx, and that thing applied to itself. Okay, what do we do with this? Well, all we can do is do a beta reduction. So let's do a beta reduction and apply the second of these expressions to the first, so that it gets bound to the x. So we have lambda x. So now we'll get the body E applied to x of x, where these x's, each x is now the second expression there, the lambda x dot E xx. Okay, what do we do now? Oh, wait a moment. Before we do anything, look at the expression following the E. We've seen that before. It's the same thing that we have in the line above. But that's exactly P. That's what we defined P to be. In other words, P in one reduction step reduces to E applied to P. In other words, they're convertible to each other. They're essentially equivalent in the lambda calculus. So E applied to P is P. That's the fixed point that we're looking for. Notice that we made no assumption whatsoever on E, what it looks like. So that means that this magical Y combinator can always be used to find a fixed point of an arbitrary lambda expression. For any E, YE is convertible to E applied to Y of E. Well, how does this thing work? Let's have a closer look. Recall omega. We saw that last week. Omega was lambda x dot xx applied to itself. Remember that in a single beta reduction, we get omega back again. In other words, by beta reduction, we never arrive at a normal form. Let's take a closer look at what this is. We have omega, and it's applying this expression, lambda x dot xx. xx is essentially the body of this loop, this infinite loop. Well, loops are pretty cool in programming languages as long as you have a way of breaking out of the loop. So suppose instead of just running this loop infinitely, we take this loop and pass it to some function f. And then f can decide whether to continue looping or to break out of the loop. Well, if we look at what the magical Y combinator is doing, it's doing exactly that. We've taken omega and we've passed in, before we execute the loop, we pass x of x to a function f. And f can decide to do a little bit of work and then either continue looping or exit the loop. Now this is cool. So this is exactly what Y is doing. It looks magical, but if you dive into it, you see, essentially we're building a loop with an exit condition. So Y is just inserting some productive work into the body of omega. Let's see how we can use the Y combinator. Have a look at some of these expressions. So suppose we take the function f, which takes an arbitrary x and returns true. So it's essentially a constant function. For any argument, it will return true. Let's take the fixed point of that. Y applied to f. We can use the fixed point theorem by, we know the fact that any y, when y is applied to any lambda expression, that's equivalent to that function applied to y of f. So let's use that from the fixed point theorem. So we save ourselves some work in figuring out the beta reduction. We simply use that fact. But that's now f applied to something, and f is a constant function. It always returns true. In other words, the fixed point of f is true. That makes sense. If we apply f to true, it will give true back. And this holds no notice for an arbitrary constant function. So if we have any function, lambda x dot k, where k is a constant being returned, then the fixed point of that function will be k. And the magical Y combinator gives us that back. Now let's look at our successor function. Recall the successor function that we had defined a little bit earlier. If we apply y to that, by the fixed point theory, that's going to be the same as successor applied to y of successor. In other words, that'll give us the tuple, false, and y of successor. Now, I ask you to consider, what are the successor and predecessor of this strange value, and what does this represent? Let's have a look at that again in the question and answer session. Now we have all the pieces we need to solve our problem of how to model arithmetic in the lambda calculus. We have our R plus combinator, so it's a closed expression. It's an abstraction over our plus function. What we really want is the fixed point of that guy. So let's simply apply the lambda expression y, our magical fixed point combinator, to R plus, and that should give us the plus that we want. It is the fixed point, because that will guarantee when we pass plus into R plus, the result will again be the plus function. That's exactly what we want. So let's step through the execution of plus of 1 and 1. Plus is R applied to R plus, and we're passing it the values 1 and 1. Recall that we're using our encoding of numbers here. So each of these 1s is not the actual number 1, but our encoding of 1 in the lambda calculus, so the successor of 0. This is the same using the fixed point theorem of R plus applied to plus, and that applied to 1 and 1. Expanding that, the body of R plus is going to be, once we pass in plus, is going to be is 0 of 1, and then two arguments, either 1 or plus of predecessor 1 and successor of 1. Well, 1 is not 0, that's false. So now false gets these two values. It throws away its first argument and returns the second argument. In other words, plus applied to predecessor of 1 and successor of 1. Looks good so far. Let's continue. Plus, by the fixed point theorem, is R plus of plus, and we pass it its two arguments. We expand the body again as before, so that's is 0 of predecessor of 1 and successor of 1, and this big expression that follows. The predecessor of 1 is 0, so if we pass that to is 0, well, is 0 is going to return true, and now true gets successor of 1, and it's a big expression, but it throws away the second part and will return successor of 1. Well, what's successor of 1? That's 2 in our encoding. So it's working exactly as we expect. So far, so good. We have shown that we can implement addition in the lambda calculus using our encodings. It's a simple exercise now to model subtraction, multiplication, and lots of other operators. But let's take a slight diversion here. We have our lambda calculus, and so far we never talked about types. So it is what we might call an untyped language, because there's only one type of thing, which is a lambda. There are lots of variants of the lambda calculus. The typed lambda calculus looks exactly like the lambda calculus, but all it does is it adds a little superscript that describes what kind of an object it is. So we have essentially two things we want to model. One is the fact that some variable x may be of some type, tau. If we have a lambda expression is an arrow function from some type tau2 to type tau1, and its argument must match the argument type tau2. So e1 applied to e2, the e1 must be of type tau1, arrow tau2, and its argument must have a type that matches. It must be of type tau2, otherwise the type is incorrect. And a lambda x, well, that x must be of type tau2, and the body must be of type tau1, and then if we have such a lambda, the type of that whole lambda is tau2, arrow tau1. For the rest, it's exactly the same. If we erase the superscripts, we just have the lambda calculus that we had before. So all we're doing is extra bookkeeping. That's all that we have here. Let's look at the alpha, beta, and eta rules. They are exactly as we had before. The only difference is we're doing extra bookkeeping in the superscripts. So I've an alpha conversion, lambda x dot e. Well, the x is of type tau2 and the e is of type tau1. When we rename the x's to y's, the only thing we want to be sure of is that the type of y is the same as the type of x. So they're both tau 2. So this rather messy looking alpha conversion is just doing what we did before, but ensuring that the y and the x's are of the same type. The beta reduction is again exactly as we had before. We're just doing extra bookkeeping. And notice what we want to ensure. So if we have a lambda x dot e applied, e1 applied to an e2, the thing we have to make sure of is that the type of e2 is the same type as our x. So they're both tau 2. Otherwise we can't do the substitution. And finally, an eta is simply taking a lambda x with the body e applied to x. Those x's are the same and have to have the same type, tau 2. And then what that reduces to is the e that we had before of type tau 1. Here we have our encoding of the truth value. Remember lambda x, lambda y, lambda xy returning x. The true encoding of true will return the first of two arguments passed in. Notice the types of these things. If x is of type A and y is of type B, then the whole lambda is of type A arrow B arrow A, because the thing that we'll get back in the end is the x, which is of type A. Notice what this means. That means if we want to apply our truth values to different ranges of values, then they'll all have to be typed. So instead of having a single polymorphic truth value, we're going to have a single truth value for every different kind of argument that we want to pass in. This is exactly the disadvantage that we have in simple monomorphic programming languages like Pascal, where we cannot write a generic sort function. We need a different sort function for all different types of lists of things that we want to sort. So let's have a look at what the polymorphic lambda calculus would look like. Once again, we have a calculus which looks just like our original calculus. If we erase all of the fancy annotations, we'll get the original lambda calculus back, the untyped lambda calculus. What we're doing now is we have, again, annotations that express types. The only difference is that now we add type variables, just like we have in Haskell. So instead of having a monomorphic lambda calculus with fixed types, we also have type variables. So this is really close to what we have in Haskell, and this allows us to model generic functions, just like we have generic classes in Java. So polymorphic functions like map and sort, they cannot be typed in the typed lambda calculus. You need typed variables. I'm not going to show you all of the semantic rules. Let's just look at the beta reduction. So beta reduction, lambda x dot e1 applied to e2. We're going to give the type e1 and e2 concrete types tau 1 and tau 2, but we're going to give x a generic type, nu. And now all we want to, if we do a beta reduction here, we actually do two substitutions. We want to substitute for every x in the body e1, the value e2. But first, before we do that, or after we do that, we want to bind the type nu, which is a generic type, a type variable, to the concrete type tau 2. And that's why on the right-hand side of the arrow here, we see a substitution not only of e2 for x, but also a substitution of the type tau 2, our concrete type, for the type variable nu. So for the rest, it's exactly the same as we had before in our untyped lambda calculus. It's just that we do the extra bookkeeping, and now we have a binding that binds a type variable to a concrete type. Now we've recovered what we just lost. So now I can have a completely generic truth value, which is expressed in terms of type variables alpha and beta. So we have, as before, a lambda x, lambda y dot x, as we had in the untyped lambda calculus, except that x and y have the generic types of type variables alpha and beta. And the type of our truth value is going to be alpha arrow, beta arrow, alpha. Now we can apply it to concrete values a and b of types big A and big B, and not only will true return the first value, that is a, but the generic type alpha, the type variable, gets bound to the concrete type big A in the beta reduction. So that looks good. Let's think back now a moment to the Hindley-Milner type polymorphism, inference algorithm. So with Hindley-Milner polymorphism, the type inference works by inferring type annotations for a slightly restricted subcalculus of polymorphic functions. Now look at this little function here, double len. Double len takes two length functions as arguments, len and len prime, and two lists, xs and ys. So a list of x's and a list of y's. And it returns the sum of the lengths of the two lists. Len applied to xs and len prime applied to the y's. So we can now compute double len of length and length applied to the string AAA and the list 1, 2, 3. This works perfectly fine. The same function length gets specialized. They're generic. Recall, length is a generic function that'll work on any kind of list. The first one is going to get specialized to work with character arrays, the string AAA, and the second one's type is going to be specialized to work with lists of numbers. You think, well, why are we instantiating length twice? Couldn't I define this double len of len, x's and y's, and then just compute the sum of the length of the x's and the length of the y's? Unfortunately, that won't work. So the Hindley-Milner type inference is going to look at this, it's going to look at the length function, and it's going to get super confused. You say, what's the type of length now? Is this length going to be specialized for numbers or for lists of characters? And it won't know what to do. So this is going to give us a type error. So this is this shows us the limits of the Hindley-Milner type inference. And typically when you get programs that you think should work perfectly well, but they don't, the type error that you get is because you're trying to take something that's generic and its type gets specialized in two different ways. Let's return to self-application. We had two examples of self-application, one in omega and the other in the y combinator. Both of them had a lambda x where somewhere in the body x was being applied to itself. So here's a puzzle for you. What kind of type annotation would you assign to lambda x dot xx, or in general, x applied to x? Let's save this as well for the question and answer Zoom. As we'll see, it's pretty much impossible to come up with a reasonable type with for self-application given the kind of type notions that we have so far. As a consequence, the y combinator cannot be written in Haskell. If you try and program it, Haskell is going to complain. So, as a consequence, most programming languages, instead of giving you something like the y combinator, they offer you a built-in mechanism for defining recursive functions. And it requires its own, essentially, its own rule. Here's what you might do in the lambda calculus to avoid the need for y. We introduce a new syntactic construct that looks like lambda but is slightly different. It's called def. So def f.e will define a function f so that f can be used anywhere in the body big E. When you apply that to some value e, what happens is that you unfold the definition. Unfolding simply takes this expression def f dot e and replaces it for every f found in big E. Well, that sounds pretty weird. What you're doing essentially is you're taking the definition and you're pushing it into the body. So everywhere in the body where you had f before, simply the syntactic structure f, you now have the definition of the function. So you duplicate the definition of the function within its body itself. So if it's used once, it gets pushed down one level. If it's used multiple times, it gets pushed down multiple times. And now every time you actually need that function, you again simply unfold it by pushing it down. This is a little bit like what the Y Combinator is doing in a more primitive way, but now you've made it an addition to the language itself. So let's have a look. How would you now use this to define the plus function in this extended lambda calculus? So the parts in red here are the usages of this new def feature. So now we define plus, we say def plus, its body is going to be, there's a difference now between def and lambda. Def is combining the lambda, what we did before with the lambda abstraction and the Y Combinator. Now it's a built-in. So we say def plus. The definition of plus is lambda nm dot is0 nm. Here we're using plus recursively, applied to predecessor of n and successor of n. Now that big red thing is applied to 2 and 3. In order to do a beta reduction, well, we can't yet. We need to take this great big red thing and apply the rule we see just above to unfold it one level. And now we'll get a lambda, and then we can use ordinary beta reduction. So we do one unfolding, and now we get an ordinary lambda, lambda nm is 0, blah, blah, blah. And where the f was before, now that definition has been pushed down and unfolded. Now with this lambda, we can simply do an ordinary beta reduction and bind n to 2. Yes, we do a beta reduction. Actually, we do 2 of them. We bind the m to 2 and 3. And now we get is 0, 2, and 3, blah, blah, blah. Is 0 makes a decision, decides that we need that 2 is not equal to 0, and we get the def plus expression. Once again, we get our definition at the head in order to head of our expression, and once again we have to unfold the definition. So this continues like that, unfolding the definition, doing ordinary beta reductions, and every time you encounter a recursive application of the function, unfolding it again. So now we have a more powerful language. If you look at languages like Lisp, they also have a recursive, a let-rec operator built in. In Haskell, we have the same thing. When we define a function, we're essentially doing what we see described on this, in this rule. That's pretty much everything I wanted to tell you about the lambda calculus. Let me show you quickly a little bit about some other calculi. This is featherweight Java. It's a little bit more complicated than the lambda calculus, but it still all fits onto one slide very easily. We have a syntax for featherweight Java. Here we're modeling in this calculus only the core concepts of Java which are relevant for the type system. So we have classes here, we have inheritance, we can define a super, we have constructors. So the classes are the group CL, the constructors are the group K, we have methods M, and we have expressions E. We have some subtyping rules, so every class C is a subtype of itself, and if C is a subclass of D and D is a subclass of E, or subtype, then C is a subtype of E, and so on. We also have further rules to reason about typing on the right-hand side, and we have the equivalent of beta reduction down on the bottom left in computation. In fact, if you see the middle rule labeled R invoke, That's essentially our beta reduction rule. It says that if a method has a particular body and we're applying a method to some arguments, then we do a reduction, that's the arrow there. We do a substitution of occurrences of the arguments of the formal parameters of the method by particular values, and the replacement of this by an instance of itself, described as a new expression. So I don't expect you to be following all of this. It's just to point out that all that we're doing here in featherweight Java is building up kind of a lambda calculus, which is modeling what's going on, parts of what are going on in Java. Now, the reason featherweight Java is interesting is that fairly early on in the evolution of the Java language, there were great calls to extend the Java language to have not only subtyping, but to add generics. They didn't exist in the first few versions of the Java language. But Sun Microsystems, who was originally developed and was supporting the Java language, was very reluctant to make changes to the design which might break old programs. Now, what Igarashi and his colleagues did is, with featherweight Java, they were able to prove that by adding generics to featherweight Java, you would get another language, which, if you erase the type declarations, you'd get back what you had before. In other words, they could guarantee that by adding generics, you wouldn't break old code. This was a convincing argument, and as a consequence, Sun actually changed the Java language to add generics, and it was thanks to this work with the calculus that they could be sure that this was a safe thing to do. Lots of other calculi have been developed over the years, so-called object calculi that model inheritance and subtyping. There are process calculi which model concurrency and communication between concurrent agents or processes, and there are even distributed calculi which model agents that can move between distributed nodes in a network, where you explicitly model the possibility of failure. The last thing I want to show you very quickly is the pi calculus, which is a process calculus. I don't expect you to understand everything on this slide here. I just want you to appreciate the fact that there's a new concept that's being modeled here, which is called a channel. So here we have channels, so X is a channel, and you can send along a channel a value as output or receive as input. The receiving as input is like a lambda, except now we have many lambdas. Every single channel through which we can communicate between processes is a kind of a lambda. And the new channel construct models the scope for which a channel is visible. So in this expression here, X is scoped in the left-hand part of the whole expression up to the OR bar followed by ZV. And what we want to happen here is we want to output the value Z along the channel X and then consume it on the right-hand side of the OR bar by X of Y. So the output Z is going to be bound to the argument Y. This is just like a lambda, except now we're communicating between two expressions. The first one, after outputting, turns into 0, which is the dead process, and the second one turns to its body, which is y of x dot xy dot 0, but the value y is going to get bound to z. Y is now being used as a channel, so we've taken a generic lambda, and now we've passed in this value z, and now we want to output across the channel z. We want to output x. The problem is we can't output x because the scope of x is within this new expression, the new of x. So the way that's solved is that the expression on the right-hand side, zv dot v, etc., it can migrate to within the scope of the new channel declaration by essentially performing an alpha conversion. So what was called z before is No, what was called V is now going to get renamed to X. So it migrates in and we complete our final communication along the channel X, and then all the processes are dead. So once again, I don't expect you to follow all this in detail. In fact, after seeing the slide, you can forget about it because it won't be on the exam. I just want to illustrate to you that the basis of the lambda calculus has been extremely influential in the design of many different kinds of calculi that have been used to model a great series of other important features of programming languages. Thanks for your attention.